Okay, so good afternoon, everyone. On behalf of the CMU Portugal program, let me thank you for the almost 300 participants that we have for this call. Also, thank you, Professor Jamie Callan from Carnegie Mellon University for his availability to give this talk. This talk will be part of a series of talks that we have named Data Science Talks at Carnegie Mellon Portugal program. They will take place during February and March, leading up to the advanced training program in data science and machine learning. The session will have a duration of 1 hour, 45 minutes for the presentation of Professor Jamie, and 15 minutes for questions. Please keep your microphone muted all the time and camera turned off. If you have a question, please use the chat. Identify yourself and your affiliation also. So I will now give the floor to Professor João Magalhães from Universidade Nova to give a brief introduction of Professor Jamie. Once again, thank you, Professor Jamie, and thank you all.
Thank you, João. Good afternoon to everyone. It's my pleasure to welcome you all to the first talk under the initiative of Data Science Talks at CMU Portugal. Just like João Fomega described, this is a series of webinars that will be organized under the framework of the Advanced Training Program in Data Science and Machine Learning of the CMU Portugal program. So this initiative, the Data Science Program, is a joint initiative between CMU, Nova University, and IST and the Faculty of Sciences of the Lisbon University. So today we are here for the first online talk given by Jamie Callan. It's really a great pleasure for myself to introduce Jamie. So Jamie is a professor and is currently the Interim Director of the Language Technologies Institute, a graduate department at CMU of Computer Science. And most importantly, so Jamie is one of the founding fathers of search technologies. So he has always been present in the front line of search advances, making landmark contributions to search engine architectures and complex query processing. And more recently, his research concerns neural information retrieval, the use of structured knowledge for open domain search, and the topic of today's talk, conversational information seeking. So that is the topic of today's talk. And without any further ado, I will pass the floor to Jamie. Jamie, the floor is yours. Thank you very much.
Thanks, João. I'm happy to be here. I take exception to one thing. I don't think I'm old enough to be one of the founding fathers of search. I hope not, but otherwise, thank you very much. I really appreciate the introduction. I'm flattered. So I'm pleased to be here to talk to you guys today about conversational assistants for complex search tasks. So let's dive in. Everybody encounters chat systems, dialogue systems, virtual assistants in their daily lives now. So over on the right side of the screen, I have some familiar dialogue assistants or dialogue systems that most of us run into: Siri or Cortana, Google Assistant, Amazon Alexa. And we also encounter chatbots when we go to many sites today, financial sites or other sites where chatbots may be the first line of customer support. And these systems often work very well. At least they work well for very common tasks. They have a very strong model of typical tasks that people are trying to accomplish. So people are trying to buy airline tickets, and there's a set of steps that they typically go through, or they're trying to return a product, and there's a set of questions that need to be answered before they are allowed to do that. Often they rely on extensive curated domain knowledge. So typically we often encounter them in customer support situations where the organization knows quite a lot about the kinds of tasks people are trying to accomplish. And even on your phone or with your Alexa, again, common tasks, right? For Siri, people are trying to post calendar entries. For Alexa, they're trying to They're trying to set timers. They're trying to play music. They're asking questions. But the questions that we ask and get answered through these devices typically are fairly simple, and they're the same questions everybody else asks, right? We're interested in knowing Kim Kardashian's birthday, or something else. It's sort of typical knowledge or typical trivia questions that a large number of people are interested in. And so the organizations that provide these services have a set of curated responses that they can reliably deliver for these different requests and actions. If you ask something that they aren't prepared for, that goes outside of their domain model, then often they'll use a search engine as a last resort. Probably many of you have encountered this with Siri or with Alexa. And two things can happen here. Often the first line of defense is, again, they go to a curated resource, but now it's something larger. So if possible, Alexa would like to give you an answer from Wikipedia, because we kind of trust Wikipedia. Wikipedia is written fairly well, but if you ask the right kind of question, something that's unusual enough, then you may see it going to open domain search. It's going to a traditional web search engine, and the response you get back will be more variable, right? It might be kind of strange. And people are beginning to use these more and more for accessing search engines. What's the most common interface to the web these days? It's this, right? It's your mobile phone. And yeah, it's got a screen on it, but it's not a great screen. And what I'd really like to do is just talk to the system a lot of the times. The problem is that there are tasks that we all do that really benefit from having a laptop or a larger screen in front of us. If you're trying to learn about a complex subject, someone in your family has a terrible disease, they just came down with it, you want to learn about it, or maybe you want to fix something, then you need probably to submit a bunch of queries to a search engine and look at a bunch of documents that come back in order to learn about that topic. There isn't really, if you think about asking Alexa something, there isn't really a one paragraph answer to that question that will answer your needs. Now, I don't mean to say that this is an impossible task to do verbally. We all do it verbally, right? I could call up my mother or my sister or one of you, and we could have a conversation about how to accomplish some task or about learning about a topic. So if someone in my family has breast cancer, I could call and talk to someone whose family had breast cancer, and they could answer all my questions. So we know that these can be accomplished verbally, but today's systems aren't very good at that. And so the purpose of today's talk is to bring you up to speed on an attempt to advance the state of the art in this area, to develop dialogue systems that can handle anything, just like Google can, right? You can ask about anything you want, so open domain, but allow people to really come up to speed quickly on a new topic, to learn meaningful information. So here is an example of two dialogues. I'll be talking much more about these, but you really can't imagine having these with Siri or Alexa today. So in this first one, someone is trying to learn about throat cancer, lung cancer, esophageal cancer, and they're trying to learn about, is it treatable? What are the symptoms? What are the signs of it? And the goal here is really to learn a lot about this topic. Over here, someone is interested in nominal GDP, actually, what is GDP? I should know this off the top of my head, but I'm drawing a blank. So GDP, why is it not a great measure? Gross domestic product. See, I do know it. Why is it not a good measure? What's the difference with the real domestic product? Okay, so these are things, so following the changes in the language here is difficult for today's systems. And then this is a complicated topic to give information back on. You could give back short answers to this. People would do that, but today's systems have a hard time with that. What is especially interesting here is you could imagine a medical system answering these questions. You could imagine a system that's designed for economics or for statistics to answer these questions. It's hard to imagine Siri or Alexa answering, handling this dialogue for one person and handling this dialogue for another. Because in that case, there's no underlying domain model. There may be a model here of how people seek information, but there isn't a model of medicine or cancer and symptoms and treatments. There isn't a model of the different aspects of economic measures. We have to get everything out of the text, and today's systems aren't very good at that. So what I'm going to talk about today, what I'm really focusing on, is the TREC Conversational Assistants track, CAST. Now, if you haven't encountered TREC before, this is an annual international forum that focuses research attention on tasks that are state-of-the-art, on new problems that we would like to get people working on. And the forum is shown here. Researchers design 6 to 8 challenge problems. These are called tracks, and this happens from November to May of each year. Then research groups from around the world compete. This happens in August. Usually the challenge problems are released about May, so groups have June, July, August to build their systems and prepare to compete. Then in August, usually they submit their results. NIST, the U.S. National Institute for Standards and Technology, these are the folks that worry about how you measure things. They measure how well these systems did. And they publish, well, they don't publish those results. They do this in September. And then in November every year, there's a conference where they publish the results. We find out who won, who lost. And the thing that's really cool about this is that at the conference, the participants need to say what they did, especially if you won. If your system was the best, you're expected to reveal all your secrets so that people will know how you did it, and then other people can copy your work, right? And it advances the state of the art. Now, TREC is a forum in the US. It's sort of the first of this type. In Europe, we have CLAY. In Asia, we have NTCIR. In India, we have FIRE. So these kinds of evaluation forums have become a common thing over the last 30 years. In 2019, 2020, and 21, the Conversational Assistants track was formed to focus research attention on open domain dialogue systems that support this kind of complex information seeking. So open domain means we can ask your system about anything and it needs to be able to answer it. And a complex information seeking means the kinds of dialogues I just showed you a moment ago. Joao just put in the chat that if you'd like to submit a question during the talk, please do that. Yes, please, right? That makes the talk more interesting for everybody. And I have this really nice setup here that you can't see where I can actually see the chat. I'll try and remember to look at it from time to time, so please do. So the Conversational Assistants track, this is an effort that I've been involved with Jeff Dalton at the University of Glasgow and Chenyan Jiang at Microsoft Research. The three of us put this together and we've been running it over the last several years. So the goal is to stress the state of the art and to encourage people to focus on developing this next generation technology for these kinds of systems. Now you might be thinking, I don't really care about helping Google or Amazon or Apple, right? They have plenty of money on their own, and that's true. But these technologies can be used for other companies as well, smaller companies. In fact, I'm just beginning a project to use this kind of technology for a large aircraft manufacturer. So these kinds of chat answering systems, customer support systems are very widespread, and it's not just the big major companies that have these needs, but lots of other companies as well. Okay, so what does the model of complex information seeking look like for CAST? How do we define this task? So the dialogues are going to be 8 to 12 related questions in text, just like what I showed you a few minutes ago in the throat cancer example and in the GDP example. The goal is to model a person who's trying to learn about a subject, and a sort of complex subject. We're not trying to learn about the Kardashians, right? We're trying to learn about something that's a little bit complicated. And I don't have anything against the Kardashians, except that there's lots of information about the Kardashians and a lot of really well curated information about that. We'd like to be able to also support questions about things that are less popular, right? That don't have 1 million people a day asking those questions. Their text, speech recognition is important, but that's kind of its own separate problem. So we're going to assume for the purposes of this task that we have perfect speech recognition. And I know that's not true in the real world, but if we're doing a web system, for example, many customer support systems, then the questions would come in text. The answers are going to be brief passages from a search engine. We've done this to make it, again, a little bit simpler. Also because this task, the TREC forum, attracts people who are experts in search. So the goal is the first stage of one of these systems would be a search engine is going to go into a corpus that may have millions of documents and pull out the things that it thinks are the best answers. Now, in your real system, we might not read these to the user. In these systems, we're going to assume that they do, that they're sort of paragraph length, and Alexa reads this back. But if you were building a real system designed for customer support environment, they might be something that you would pass off to a natural language processing system. Maybe you pass off the top 5 passages, and then it summarizes them or extracts the answer from them, or tries to improve the quality a little bit more before passing them off to the user. So the goal is that these systems need to return a very small set of really high quality information. Maybe we trust the information well enough, or maybe we have no choice and we just have to show the best result to the user, or maybe it gets passed to some downstream component. The corpus here, we're going to look at 2. We have MS Marco. This is 8.6 million question answering passages from Microsoft. This is a standard resource that Microsoft has made available for answering questions about a wide variety of topics. And in fact, many of the answers, well, I'm not going to show you many answers, but some of the answers I'll show you probably come from Marco. And then we also have 30 million Wikipedia paragraphs. Basically, Wikipedia pages have been taken and broken up into paragraph units. So they're not always the first paragraph of the page. They might be something from deeper in the page. That may be where the answer comes from. And then we'll measure the system quality by their first 3 passages. So they don't get credit. Well, I'll show you some metrics that do give credit for deeper down in the rankings. But really the official metrics focus on either the best, the first passage, how well did you do on the first passage, or how well did you do in the top 3. Okay, so simple model, but designed to push the state of the art here. Now, these are called topics. That's the way TREC describes these things. So a TREC topic, or a dialogue, that's how we'll think about it, is the model of a person learning about a subject. You've already seen the throat cancer and the GDP examples. I'll show you just a few more to give you a sense. And these are all real examples that our systems, the systems that participated in TREC had to do last year or this year. So here we have a bunch of questions about Social Security in the US and the history of it, who received the first check, when did the government start borrowing from it, and so on. One of the things to notice about this, I mean, you're not sitting in front of a search engine, but if you enter these questions into a traditional search engine, so BM25, if you're familiar with the research literature, or if you're familiar with Solr or Elasticsearch or Lucene, the standard ranking algorithms that are in these search engines, most of these questions are going to do quite poorly, partly because we have some ambiguity, like was it mandatory? What was what mandatory? But even if you don't have that problem, who received the first check? This is actually a tough question for these systems to answer. Most of these systems are going to focus on how you get your first check, but they're not going to give you the history. So these are actually tough questions, even though they may not look so difficult. So someone asks, does CAST encompass conversations or simply question-answer pairs? Well, you can see that in this example, I hope. So in order to understand this question, you need to understand the history, right? Was it mandatory? You need to know something about the previous questions. And that's true as we go down throughout this. In order to understand any of these questions, can it be fixed? You need to understand the history here. Some of these are fairly simple, like maybe just replacing it with Social Security. But as you'll see in some of these, perhaps the topics shift as they do in real conversations. So maybe these will talk about, well, in fact, when we saw, going back to cancer, we start with throat cancer, then we go to lung cancer, then we go to esophageal cancer. So they're all about cancer, but they're about different aspects of cancer. And if your system stays stuck on throat cancer deeper in the dialogue, it's probably going to do poorly. So you do need to understand something about the evolution of the dialogue. And I don't know if I have any examples right here, but I'll show you some later. Some of the questions also refer to the answer. So this question here could refer to something that was in one of the answer passages, but you can't figure that out by looking at the past questions. You also have to know about the answers. So sorry, that's a long answer. Does that answer your question? Great. So since CAS topics are divided into topics, it's not measuring the ability of systems to detect topic changes. I'll show you a slide late in the talk when I get to experimental results to show you that a little bit. We don't measure it directly, but we do measure the success of systems turn by turn. And what you'll see is that some turns are easier for the systems and some turns are harder for the systems. And although we don't directly tie it to topic shifts, we should do that. One of the reasons that they're harder later in the conversations is because of things like this. We've got a system that has been asked about esophageal cancer, but what it's remembering is throat cancer. And so it's answering this question and it's returning a confused answer to the user. So we see that late in the conversations, systems that can't forget at the right time tend to have lower accuracy because they're answering the wrong question. So it's indirect. Does that make sense? Great. Couldn't you also have answers to have access to the answers in the history context? Yes, well, sort of. I can't remember now why. You know how it is when you design things a year ago. You make decisions and then you're like, why did we do that? I think, well, I'll make up an answer on the spot. I think it's correct. We don't tell the system what the answer was to previous questions. Instead, we tell it what was the 5 documents or the 5 passages retrieved for the last question and the question before that and the question before that. And then it must figure out what was the answer in those documents, in those passages, and then refer to that. Why do we do this? Well, partly to be mean to the systems, right? We want to make the task harder. But also remember earlier I said that we don't imagine that the system always returns the passage to the user, the best passage. We might take that group of the top 5 and pass them downstream to an NLP system. And so the best sentence might not be any particular sentence in the answer. Its roots might be in one of those passages. Now, even then, probably a good system would know what it just said to the user. So it would be a little simpler if we told it this is what was read back to the user, but we don't do that. The systems have to figure out, in this group of top ranked passages, what sentence was probably the one that contained the answer. You're welcome. Okay, so you saw those questions, those dialogues. Here we have some more dialogues. So Social Security, I talked about that. This is about saving for a child's college education, and it talks about 529 plans, which are a particular savings vehicle in the United States. And this just shows 2 aspects of this. So I've already pointed out that was it mandatory? It refers to Social Security. In this one, how much of an increase? This refers to something that was in one of the previous answers. So this, can it be fixed? This talks about tax increases. And now this asks how much of a tax increase, right? So if you were writing a human version of this, or we call it a resolved question, a resolved question, so it has all of the ambiguity removed, it would be how much of a tax increase, okay? So you see that we have to refer to 2 kinds of context here. Okay, this just shows a sample answer passage. So what is throat cancer? This shows the typical answer passage that these systems would be working with. This comes from Marco, the Microsoft Answer Reading Comprehension, I think, or Automatic Reading Comprehension corpus. You can see this looks like it probably comes from Wikipedia. A lot of the Marco answers, these are human-generated answers. But probably the person who wrote this answer went to Wikipedia or some other medical resource and just copied out a chunk of text. And that's what you see here. And this is an okay response. If Alexa read this back to you, it's kind of boring, but it answers your question. It's okay. Okay, so most CAS systems have 2 main components. There's query or question rewriting. Really, question rewriting is what it is, but people refer to it this way, query rewriting. So is it treatable? Gets turned into, is throat cancer treatable? What is the largest? What is the largest shark? How old is he? How old is Barron Trump? And so we have this first stage to come up with a better question or query, and then passage ranking systems. So I'm going to tell you a little bit about both of these. The goal today is not to give you deep technical details because we're a large audience and people have different backgrounds. The goal is to give you a sense of how these things work and sort of what the state of the art is right now. So first we'll talk about question or query rewriting. As I've already said, the current question may refer to a concept in an earlier question or answer. May, right? It might not. So what causes throat cancer? This is a great question. It's complete and it's unambiguous. The right thing to do is don't touch it. So that's the first thing, right? It's like medicine for doctors, right? First, do no harm. That's the case here as well. Sometimes your system should just leave it alone, but that's hard. Most of our systems want to change everything. They have a difficult time deciding whether a question is good enough. So is it treatable? That refers to an earlier question about throat cancer. What is the largest? That refers to an earlier question about sharks. Why do I have both of these? Because this looks the same, right? Here we have an explicit sign. Is it treatable? So we have a pronoun or something that signals that there's a missing concept here that refers to a previous answer or question. And this is an easier case. Systems do pretty well on this. What is the largest? There's no explicit signal here that something is missing from this sentence. We know that something's missing. There's no noun here, no noun phrase, but it's harder for systems to notice that something's missing. And you could think about, if you're familiar with parts of speech, you could say, okay, no noun phrase here, so I know I need a noun phrase. But there are other questions like this where there is a noun phrase, but still, in order to really resolve it correctly, you need to know something about the previous context. So those are harder. And then how much of an increase, that refers to an earlier answer about taxes. So a good query rewriter needs to deal with a bunch of different types of problems. Most systems rewrite most questions to be better search queries. And I've already mentioned this. An added complication is that the system doesn't really know what the answer passage was for the earlier sentences. Let's see here. Are there possibilities, I missed this question. So are there possibilities to maintain or even improve effectiveness over the course of the conversation as the information need unfolds? Yes, great idea, great question. As humans, after you ask me 3 or 4 or 5 questions, I have a pretty good idea what you're asking about. And so I can make guesses about the kinds of things you would be interested in using domain knowledge and do a better job of answering your questions. These systems should be able to do that too. After the 4th question, not only do they know all the answers, but they've seen the top 100 documents retrieved for all of those questions. So they have the opportunity to build themselves a little domain model and know quite a lot about the topic, to build a little knowledge base. None of today's systems do that. That's a hard problem, but I think that the next generation systems will be doing that. It just makes sense, right? The more your system knows about the topic, the better it can be at anticipating and guiding. Oftentimes, we are asking these questions about topics we don't know very well. And as somebody who writes these topics, I kind of have to learn about the topic in order to write good questions. So in reality, if we were doing this with Alexa, a lot of the questions would be lower quality than what I'm showing you. A good system should guide you. It should say, if you ask about breast cancer, it should say, gee, that's a pretty general question. Are you interested in symptoms or diagnoses or treatment, right? And kind of guide you through the topic. That's what a good librarian or a good friend would do. These systems aren't able to do that yet, but I think we'll be seeing that in the coming years. And can answers vary between factoids and full definitions? We try really hard to avoid factoid questions because the technology for doing that's pretty well defined. Definitions, we have some of those, you've seen them. We try to avoid definitions too, because again, there are pretty good techniques for doing that. We're really more interested in somebody exploring a topic and where those techniques would fail or not be as successful. Okay, so onward. So the CAS systems used a variety of query rewriting methods. This graph over on the right side This is from an overview paper about the CAS 2020. This paper will be published in February. But if you look at the one from the previous year, you'll see a similar graph. This, along the x-axis, we have different techniques, very high-level technique descriptions that groups used. What we see here on this axis is the percentage of groups that are using it. So you can see that a large number of groups used query expansion, for example, and a smaller number of groups used nothing, because that never worked. Over here, you can see what is the relative gain using a particular metric, NDCG at 3, from using these techniques. So query expansion, lots of groups did it, but it didn't help a lot. Some, I mean, we're getting a 15% improvement over not doing it. You can see people using NLP toolkits, that works a little bit better. Over here, we see generative techniques that worked very well. I'll talk a little bit about this. I don't have time to cover all of these. And if you're familiar with this area, you probably have an idea what NLP toolkits look like. These are the systems that are going to be trying to map it to a term. And that works well, although it's narrow. So I won't talk about all of these things. But you can see that groups tried a variety of techniques, and some of them worked better than others. And this is averaged over a bunch of systems. This is not just one system. This is all the groups that did this particular approach. So I'll start off talking about a heuristic method. This is very simple. These weren't super effective, but just to give you a sense of some of the things people tried and how they thought about it. So this is one using query context. So we would assume that the first question, Q first, establishes the subject. So here, I know this is a small font. When did Social Security start in the US? So we could say that we're going to use all of this question, or optionally, we could pick just the most important terms from this question. So instead of when did Social Security start in the US, we just pull out Social Security. How do we know to pull out Social Security? Good question. This is your, use your favorite method here. So you might use noun phrases. So that would give you Social Security and US. And then you might say US is a very common expression based on term frequency, IDF, or something else. And so maybe I don't care about that. Or maybe you keep it. Maybe instead of just having Social Security, maybe you would have Social Security US. So people tried all kinds of heuristic things here in order to establish the context. This technique worked very well in 2019 because the dialogues were simpler in 2019. In 2020, we saw people doing that, so we designed more dialogues where that strategy will fail, where the topic shifts more. And so depending on the kinds of conversations you have, this could be a great strategy or not a great strategy. In this Social Security example, that would actually work very well. If you just append Social Security to every question, and even if you have US there, you would do very well. So you would append these to the current question. So the current question is how much is owed, and we either append the full original question or just the phrase we selected. Now these look terrible to us, but we're not showing these to the user. We're just passing these off to a search engine. And these are actually great search queries. They're unambiguous. Some search engines, it depends on your search engine, but some search engines don't care a lot about the word order in the query. And so this does okay. This is just a variation of this. Instead, so I mentioned here, but I didn't say, that this works if the dialogue doesn't change direction too much. So for example, throat cancer, I showed you that this strategy would get into trouble because it would carry throat cancer all the way through the conversation. So a variation on this theme is to select the most similar question from earlier in the dialogue, okay? And then everything else stays the same here. So in that case, instead of going back to the first question, we're trying to figure out where in the dialogue we should get our context from. And that works much better for some of the dialogues like throat cancer. In this dialogue, it probably doesn't work as well because going back to the earlier question, that earlier question may also be unresolved. It may be ambiguous. So for example, if you're asking about, let's see, when will it run out of money? That will get you back to borrowing, probably that's the most similar sentence, but this doesn't have Social Security in it. So this strategy works well for some questions and not for other questions. A much more successful example is transformer methods. These were really state-of-the-art last year and this year. I won't tell you about transformers. This is a well-known technique in the field over the last couple of years, a neural technique for recognizing similar texts and widely extended for question answering and search and a variety of other tasks. What we need to know today is that a transformer, in this case, a lot of systems are using T5, it converts an input text to an output text. And it's a giant machine learning model with a zillion parameters that is trained to, given lots of examples of input texts and output texts, it learns a model. And you need a lot of data, so a lot of systems this year use the Canard data set for this. If you've seen these things before, then you're familiar with this. Basically, we're training a sequence-to-sequence model, and the idea is that the question that I would like to produce, the manually resolved version of this, or unambiguous version, well, let me say it this way. I'm trying to build a model. So out of all the possible models, I'm going to pick the best model, and that's the one that assigns the highest probability to the desired answers, given a sequence-to-sequence model that has the current utterance, the current question, and the question history, and some set of parameters. Okay, so what I'm going to do is at a particular point when I'm training the model, I have the preceding history in the dialogue. I have the current question, how much is owed. I have all the questions that came before that, and I have the desired utterance, which is how much is owed to Social Security. And so I'm going to train a model that when it sees something like this, how much is owed, it should rewrite it as how much is owed to Social Security. So it has to figure out how to go into this history and recognize the phrase that needs to be added here. Let's see here. I have a couple of questions in the chat. So do I think allowing conversational search agents to ask clarifying questions would improve effectiveness? And could this be seen as a way to rewrite or reformulate queries? Yes, absolutely. And if I'm designing a system today for industry, that's the first thing I would do. If I have a question that is ambiguous, I would just ask the user. Now, that's going to be irritating, right? We're all used to not fully specifying every question when we talk to each other. We expect an intelligent partner to remember the context. So a good system shouldn't ask for clarifications on every question, but my feeling is that every 3 or 4 or 5 questions, people would accept that. So yes, I think that's a good strategy. We don't have a way of doing that today in CAST. That's something we've talked about. What do I think about chatbots for wayfinding using Google Maps? I haven't seen anybody using chatbots for directing children to school without supervision. I think that's an interesting question. That's an example of a closed domain environment, though. We know we're talking about maps. We know there's only a limited number of things we could be talking about. So that in general is an easier problem because there's just there's a limited number of things at each turn, at each point that we could be discussing. So that's sort of an example of a more typical dialogue system. Okay, so transformer models, just kind of this is a quick overview of how they're used. Really, it's our magic machine learning box. The key is to have lots of training data to train these systems. And then they do a pretty good job. Given a new question that they've never seen before, like how does it work? We hope it will write something like how does a 529 plan work? They're not always this beautiful, but they do pretty well. And even when they write questions that aren't human looking, they may write questions that are like this, which is fine for our search engine. The search engine can work with that. So here's an example using, so this showed you using the query history or the question history. This talks about using answer documents. And really with answer documents or answer sentences, it's the same thing. We can still use our transformer models. All we need to do is extend the history to include previous answer sentences. Now, how do we know where the answer sentences are? That's a retrieval problem. So we tell our system, here's a bunch of sentences that the user has seen in the past. Here's the current question. Pick the sentence that is most, here's question 1, question 2, question 3. For question 1, which of these sentences is the best match? For question 2, which of these sentences is the best match? So we turn it into a simple search problem. It's pretty simple. You've got one question and 25 sentences. So you just rank them and pick the best one. And for the second question, same thing, pick the best of the 25 sentences. Going down, you add those to your history, this part shown right here, and then you just train your transformer model the same way, and that works pretty well. So I'm running out of time. So let me get to, I'll start going a little more quickly over some things here, which I think are more obvious. So most systems used a ranking pipeline. They used BM25, standard retrieval algorithm, everybody's favorite retrieval algorithm, found in all popular search engines, to get the top 1,000 to 5,000 documents. And then they pass that into a BERT re-ranker, which is slow and runs on GPUs, very computationally expensive, but more accurate. And that gives them the top 1,000 documents, and then they'll be judged on the top 3 or 5. This is too expensive to run on the whole corpus, so you do this first stage with BM25. Don't you get limitations on the size of the input text to the transformer model? No, not really, because what we're passing in, I didn't actually show what goes into BM25. Sorry, I forgot about that. But the input here is going to be this question, which is short, right? And then transformer models are also comparing query to answer passage. The answer passages are also short. So in practice, this does not run into problems, capacity problems in the transformer models. If we had long documents or if we had long documents, then it might be more of a problem, but it isn't a problem here. A more efficient way of doing this is to stick a learning to rank system in the middle. This improves the quality of stuff coming out of BM25 and allows you to pass a smaller amount of stuff to BERT and then to the user. If I'm building an interactive system, which I have, I do this. It looks like it would be slower because it has this extra piece, but what it does is it reduces the amount of stuff that needs to go to BERT, and that makes the system faster. Okay, so how do these systems do? This shows you the best automatic systems, no human hands touching anything. So we can see the 5, well, this isn't the best 5 systems. This is the best 5 groups. So we can see their mean reciprocal rank. This is 1 over the rank of the first correct answer. So a value of 0.6 here, which is what these first few systems are. That means that the first correct answer, the average rank was about 1.7. So they're doing pretty good. They don't get the answer at rank 1, but they get it pretty close to the top. Rank 1 or 2 most of the time. NDCG is a metric that considers passage quality. This tells us that, so there are passages that kind of answer the question, and there are passages that are great answers to the question. This tells us that they get answers or passages that kind of answer the question, but they're not always great at getting the best passages at the top. So there's still room for improvement here. And then recall, you can see that there are a bunch of questions where they just don't get the right answer. So that's kind of hidden by this. This says that they're probably getting the answer at rank 1 a lot of the time, but when they fail, they really fail. But this is pretty good. I'm actually surprised they did this well. These are the best manual systems. So here, humans rewrote the questions. Instead of having our automatic query rewriters, humans did it. And so you can see they get better scores. Now the first correct answer is about rank 1.5. NDCG scores have gone up, and recall has gone up quite a bit for the best systems, but not for everybody. So that's better, but not as much better as you might expect. If I put those results side by side here, these are the automatic systems. These are the ones that had the manual. So automatic query rewriting here, manual query rewriting here. These results, the humans win. Yay, we're still good. But they're not as much better as you'd expect. The margin isn't huge. These systems are getting the answer on average at rank 1.7. These at rank 1.5. Yeah, the results are better here, but the automatic systems are doing pretty well, or the human systems, human rewritten queries isn't enough, right? We still need more in order to get the level of accuracy we would want. This just shows how systems do throughout the conversation. You can see that the first question is easiest. It kind of has to be, because that's the one that establishes what we're talking about. Then the second question is the hardest. And it's the hardest because we don't have much context yet. All we have is the first question. And so if we need to infer something, we need to figure out what the user is talking about. We don't have a lot of history to do that with. I mean, yeah, it's unambiguous. We have just the first question. And humans would be able to do this well, but systems struggle with the second question. They do better when they get more of a history. And so you can see they do kind of okay. It turns three through 6. And then they suffer when we get down deeper in the conversation. And this usually late in the conversation is where we have major topic shifts. The user really changes direction in a significant way. And some systems just struggle with that. They don't let go. They keep remembering the prior context, and they use that to deliver the next answer. But really, the user has moved on. They're asking about something that's a little bit different. And these systems suffer because of that. And then we see some great results here for 9 and 10. I would say ignore this. Not many of the questions, not many of the conversations go that deep. And so this is probably very sparse data. It is sparse data. And special cases, I wouldn't worry too much about that. I wish I could say that after 10 questions, they get really good, but I don't believe that's the case. All right, so I need to wrap up so that you guys can ask questions. The Conversational Assistants track creates data sets that you can use for your own work. You can go download it, right? We created this not just as a competition, but really as a way of creating these data sets that other people can use for their work in industry or for their research purposes. All right, so let me finish up. CAST has this really simple model of complex information seeking. It doesn't know anything about the user. It has answers that are pretty constrained, and the questions and answers are independent of previous results. And that wouldn't be the case in a real world. But still, even in this fairly simple model, the task is realistic and it challenges today's systems. We see some areas where they do well, and we also see where they struggle a little bit. And the questions get harder as the conversation progresses. The user always assumes that the system knows what's going on, but sometimes the system doesn't, right? And so that's a challenge, especially when conversations don't progress linearly. We see examples of conversations that refer to something, shift away from it, and then come back to it. Systems really have trouble following those shifts. The current technologies aren't bad for this unrestricted open domain tasks. The question rewriters do a pretty good job. Passage ranking works pretty well. These systems certainly aren't perfect. There's lots of room for improvement, but they're better than today's commercial systems. You can throw anything at these systems and they do okay. They're not as high quality as today's commercial systems, but you can't ask today's commercial systems about anything you want. There are some changes for the future to make it more realistic. I have them listed here. I won't read them all. You can read them. The goal going forward in 2021 this year, and if we do it again next year, is to make the conversations harder and more realistic. And so, actually, I'd appreciate your feedback. During the QA session or afterwards, contact me offline. What would make these conversations more realistic? What would make them more similar to the kinds of things you encounter in your world? The groups are just beginning to get started for 2021. So, come join us in advancing the state of the art. This is an open competition where anybody can participate, and we'd love to have more people involved. The more people that get involved, the more realistic the task becomes, and also the more we learn about how to do it well. So I think that's everything I've got. Here are a few references. These are in the slide deck for people who are interested in knowing more about this. And now I'll be quiet and answer your questions. So thanks for your attention. So you can put questions in chat, or you can raise your hand and I can call on people. Either one is fine. Thank you, Joao. He put a link in the chat.
Thank you, Jamie. I believe you already answered many of the questions during the presentation, but we do have two questions here. One from Simão Gonçalves. I believe he was referring to slide 24. We are assuming that the first question establishes what we are talking about.
Yes.
Although that may be so in a lot of cases, can that be limiting in some way?
Sorry, what was that last question? The last
Although
sentence?
that may be so in a lot of cases, can't that be limiting in some way?
Oh, yes, in two ways. One is in the real world, the first question might not be well formed. And someone asked the question about clarifying questions. So really, we would like a system to recognize when it cannot give a good response because it just doesn't understand the question. And so in that case, it should either ask you to give a better question, or it could use the search results to say, I think this is what you're talking about, but you know, are you interested in this aspect of the topic or that one or some other one, and kind of guide you towards a more well-specified question. So so question quality is one issue. The other is that we have a few topics, although not enough, where it really shifts dramatically in the middle of the dialogue. And so systems need to understand that the first question established a context that no longer applies. They really need to think about something else. So I hope that answers the question.
Okay, thank you. We do have a final question. Henrique Cardoso. Do systems have to search for the right answer on the wild or from a provided Wikipedia dump or the like?
So the systems are, well, let me say it this way. Answers come from the gold standard answers all come from the two document collections that I mentioned, Marco and the Wikipedia corpus, the CAR corpus. A CAR means, it just means Wikipedia divided into two paragraphs. You can get answers. TREC has no rules. So you are permitted to get answers from any place else you want. So other websites, knowledge bases, anything you want. That's not considered cheating. In the grading is not in the grading, you need to return a passage. So you could go to a knowledge base, find an answer, and then go to the document collection to find a paragraph that contains that answer. That would be fine. We have considered for, in fact, it was on my list of things for next year, allowing more answers that come from the wild. That makes it more like a traditional question answering task, because now you have to judge the quality of the answer, but you have no support. And that can work well for some kinds of questions, but not others. So for example, if you ask, what is the tallest mountain in the world? And the system comes back and it says, you know, it's 4,000 meters, you know, okay. Or if you ask how tall is the tallest mountain and it comes back and it says 4,000 meters, you know, is that right or is it wrong? Who knows, right? In order to judge that answer, you really need a paragraph that gives the context so that the user can have some confidence in it. So at least for the next year, I think that it will still be passage based, but groups can use other resources. I hope that made sense.
Okay. We have here another question. I think we have time. Luis Góes, he asks, I noticed that most questions don't have terms such as not or outside. He gives an example. How much is not owned? What is the social security outside US? And he asks, is this a problem?
Yes. So search-based solutions are terrible at negation. And they just can't do that. This is where you would need more advanced natural language processing. So you probably need that, well, in the query rewriting stage, you would probably need that in order to produce a search query that removed the negation or converted the negation into something that the search engine can use. And then I mentioned that we imagine taking these top 5 passages, or you could take more, and passing them to a natural language processing system that would determine the final answer. And so you'd need to do that for negation, right? You'd need to be able to recognize which of the passages respond to the negation. So I think search-based solutions, like I talked about today, wouldn't be sufficient.
Okay, we have now some questions. I don't know if you have time for more.
Yeah, I do. Let me take the transformer one quickly. So I showed real quickly, I showed the ranking system that had learning to rank in the middle. The reason I put that in there, we have a system that we use in interactive settings. So you're searching over, you know, whatever that is, 12 or 13 million passages, but we want responses to come back in a couple of seconds. And so we use learning to rank in the middle of that to reduce, so BM25 returns a large set, then learning to rank reduces that down to a smaller set that can be passed to BERT, and then BERT is able to re-rank that smaller set in 2 or 3 seconds. And so you can play games with these systems by increasing the sophistication of your pipeline. You reduce the amount of data that goes into those complicated transformer models so that the system can respond quickly, and you don't lose quality. Does the system take into account the emotions? No. Good idea, but not something that we do here. The goal here is to build a reusable data set. So I put in that plug for the data set there, right? And I said, you guys can download the data and use it for yourself. But then that means that really we in order for it to be reusable, I guess we could build in a user model that says at this point, the user got frustrated, but that kind of doesn't make sense because maybe some systems, the previous response was terrible, and other systems, the previous response was good. So anyway, now we don't include that. There's a question about time-dependent questions. We don't do those now. I think, again, that would require stronger NLP, stronger natural language processing than these search-based systems have. But yeah, that would be good. And publication dates, we could use that, but we don't. But there's nothing to stop you from doing that. We just haven't done that in the conversations that we created.
Okay, I believe our time is up.
So, well, let me just ask a final question, if there are not any other questions. So, Jamie, once again, thanks a lot for the great talk. So there's plenty of idea for ready to use algorithms and techniques that you just passed on. So, and my final question is more like for PhD students that are about to start, or people that may wish to start in the future. So we see a trend where in 2019 you had BERT and they were at the top, and this year you doubled the number of parameters, and you had T5, you had encoder, decoder, you doubled the number of parameters, and it won, right? So it's no groundbreaking achievement because it's built on top of the transformer, and it's difficult for all universities to keep up with these Google platforms and Microsoft, so they have plenty of resources. So what do you think is the message that we can have for our students that would like to advance the state of the art in conversational search?
So I think there are 2 answers right now. One of them is, can we do, so there was a neural revolution when I was a graduate student, right? This is not the first neural revolution. And most of that work died off because in the beginning it was magic. And then we learned what the magic was doing. We learned what the neural methods were doing, and we figured out ways to get the same results with much simpler techniques. And the neural models were hard to train and data hungry. And so we moved to simpler models that worked as well. And so I think here also, we need to really try to figure out what these transformer models are doing, what is their secret sauce, and ask whether we can accomplish those things with simpler techniques. And I think we're seeing in some areas, not yet for query rewriting, but for some other areas, yes, actually we can get the same results with somewhat simpler techniques. Not dramatically simpler yet, but we're moving in that direction. The second thing is, I mentioned at the beginning that I'm involved in a project that is looking at how to apply these in industry setting. And in that setting, we don't have the massive models, right? We don't have the massive corpora. And so the question we'll be looking at there is, how do you train these models with small amounts of data? Is there a way to automatically train them to be as effective? Or are they just not appropriate in that environment? Do we have to use the simpler feature-based models in those environments? Google and Microsoft are hugely influential in our field, but in some sense, those are limited domains, and most of the environments that people, most of the problems that people encounter in industry and in real world settings, they aren't, they don't have web corpora of bazillions of documents. And they often do have a lot of domain knowledge that could be used to train smaller models that might be just as effective. So that's my answer. I hope it makes sense. Simpler models and models trained for smaller domains.
Does make sense. Thank you very much, Jamie. Thanks a lot.
Thank you.
Well,
okay, it was nice talking to you guys today. Thanks.
Thank you, Jamie. Bye.
Bye.
Great. So bye-bye, and thank you everyone for attending.
Thank you all. Bye.
Thank you all. Bye-bye.